Okay, so in the preamble to the second example, there's a bold note above it for you to be mindful of, which says, note that a hypothesis test should be formulated before the data are collected and not after. If the sample data leads you to form a hypothesis, then you should plan a suitable test to collect further data on which to conduct it. So with the running example that we had with the CO2 levels in Avonford, if the reporter was using the values, the 10 values presented to her by the researcher, and she used that to form her hypothesis test, then there should be a subsequent test, more data gathered in order to conduct the test. So it's just important for you to be aware of that. So the second example. A researcher is interested in establishing the mean IQ of the population and uses a test which is known to give scores with a standard deviation of 50. Initially, the researcher takes a sample of 100 people and finds the mean of their scores to be 105. Knowing that 50 years earlier the mean score of this test was 100, the researcher puts forward the theory that people are becoming more intelligent as measured by this particular test. She selects, she selects a random sample of 500 people, all of whom take the test. Their mean score is 103.22. Carry out a suitable hypothesis test on the researcher's theory at the 1% significance level. So what has happened here is that the researcher has initially taken a sample of 100 people, realized that the score is higher, has formed a hypothesis based on that, which they've then gone, or she's then gone to take an additional sample. So that situation is backing up the emboldened note above it. So you can see here, if I just write this in this area here, so the hypothesis is informed by this sample. So new sample tested. Okay, so what the researcher has done is statistically the right thing to do. First sample has given a cause to come up with a hypothesis, which she is then testing with a new sample. Okay, so here we have the random variable test score, where X is normally distributed with a mean of 100 and a standard deviation of 15. So that's our parent population. And then we have our sample population, which is normally distributed with the same mean and the standard deviation, and we're taking a random sample of 500 there. So that's the sample mean population, and from that the standard deviation, I'll stick that in red just for us to be clear, is going to be 15, which is the standard deviation of the parent population, divided by the square root of the sample size, which is 500. we then have the sample mean of 103.22 for the sample that she took. Our hypothesis test now is going to be that there is no change in intelligence measured by this test, so that the mean was 100 and is still 100. So people are no more intelligent than 50 years ago. Okay, so the null hypothesis, H0 mu is 100, people are no more intelligent now than 50 years ago. But then the alternative hypothesis, so what is this researcher saying? Her theory is that people are becoming more intelligent. Well, if they're becoming more intelligent, the mean sample will score will increase, so it will be greater than 100. So people are becoming more intelligent than 50 years ago. The alternative hypothesis is that that mean is rising. It's going to be a one-tailed test again, and this time it's a 1%, not a 0.1% significance level. So that sets it up. Once more, we're going to look at both methods. So the p-value. So with the p-value this time, we've got a mean of 100, and this here is where the 103.22, our calculated sample mean, and I want to find out what that probability is, that area there. So we're interested in the probability that x bar is greater than 103.22. If that probability is smaller than 1%, then we can reject the null hypothesis. So the p-value is going to be which we can read off our calculator. So if we go to normal cumulative, and this time we've got a lower value of 103.22. We've got an upper value of 1 times 10 to the 99. Our standard deviation is going to be 15 over the square root of 500. And the mean is 100. So we've got a value there of 7.9296 times 10 to the minus 7, which is 0.000001, 2, 3, 4, 5, 6, 1, 2, 5, 6, 7, 9, which is clearly less than 1%, which is 0.01. So reject the null hypothesis. We reject the null hypothesis. So if we go down method 2, critical region, same little sketch that we're going to do. The mean is 100. This time I want to know what value of mean is going to create a region there of 0.01 or 1%. So on my calculator this time I'm going to go back to normal, but this time inverse normal, and my area is less than, so I won't make the same mistake that I made in the previous example. What I'm actually going to be putting into my calculator is this green region, which is going to be 0.99. The rest of it remains the same, which gives me a mean value there of 101.6. So the critical region is such where the mean needs to be greater than 101.6. Our calculated mean for the sample is 103.22. So x bar is 103.22 within critical region, therefore reject the null hypothesis. So we have to say we're rejecting the null hypothesis, and then our conclusion is there is sufficient evidence to suggest that IQ scores have increased on this test. So it's important that we're putting on this test rather than saying, in general intelligence is increasing, because it's just based on the outcomes of this test. So once more, you set it up, you relate all your normal distributions, you clearly state your null and alternative hypothesis and try to give a context for that. You identify whether it's a one or a two-tailed test. If you're not instructed one way or the other, you've got a free rein as to which one of those methods you choose before declaring you're going to reject the null hypothesis and state there's sufficient evidence that the alternative hypothesis holds water.